Hello, I'm Samay Shukla. This is Lab 2 Physics 12 at Georgia Tech. Introduction. Description / aim of the lab. The aim of this lab is to measure and model the balance between gravitational force and electrostatic repulsion between two charged pieces of tape, considering distributed charges across the tape. So some of the fundamental concepts involved in the lab were similar to Lab 1, but this time we distribute the charge evenly across the length of the tape in a computational model. So rather than a point charge, we consider a line charge. Electrostatic force, so Coulomb's law, obviously, the magnitude of force between two charged particles are k, q1, q2 over r squared, where q1, q2 are the charges of the respective particles. Gravitational force, Fg is equals to mg, and in our lab's scenario, we consider equilibrium, and under that, Fe would be equals to Fg. Charge quantization. So tape's net charge comes from a deficit or surplus of electrons, and this deficit or surplus will always be an integral multiple of the minimum amount of charge that can exist, that is equals to 1.6 times 10 to the 19 power negative 19. Experiment setup. So two equal strips of clear tape were cut and suspended. One piece is fixed, the other is free to move. Both are charged by quickly pulling tape from the surface. Procedure. So you just take two strips, put them on the table, and then pull one apart. So one gets a charge, one doesn't. Then you hold one and you put the charged part tape above it, and they should repel. They should attract, and that would prevent it from slacking. And in the equilibrium, Fe would be equal to Fg. Also, you have to do a few measurements like the length and width of the tape, the mass of the tape, or you can also do density and then measure mass. And yeah, computational model. So model setup. So in lab 1, tapes are modeled as point charges, but in lab 2, charges distributed evenly along the length of each tape. It's like a line charge. So there are two parallel tapes, each of length L is separated by measured center to center distance D. Each tape carries unknown total charge Q, and we set linear charge density to be lambda, which is equals to Q over L. And we model estimates charge needed for equilibrium, F equals to Fg. Assumption. Some of the assumptions we made were there's a uniform line charge distribution along each tape. Unlike lab 1, we don't consider the tapes to be point charges. Air resistance is negligible, and we also assume that all charge across the tape is uniformly distributed. The glow script code. So this is just the beginning where we define some physical content. So we have m, that's the mass of the tape, it's the same as lab 1. Q, which is estimated net charge, and then we define a function where E field. So we pass as arguments the charged particle itself and its observation location, and we calculate E based on the electric field at the at the observation location. And then we define a function line charge, which essentially creates a line of n uniform point charges with a given total charge, which what our estimated charge was. And this occurs, so it starts as start was, which just passes an argument. And we then create the tape, so we actually create the tape objects, top tape and bottom tape, which exist as line charges, and we pass as arguments the required parameters. So we then define a few more constants, and then we do a for loop where we iterate each charge in the line charge to find the electric field and force, so that we can actually visually represent this in GlowScript. And when you run the code, it actually prints this. So this is the output, and it tells us the magnitude of electric force is 5.9 times 10 to the negative 4, and the magnitude of gravitational force is 2.8 times 10 to the negative 3. So discussion. So what if I had modeled each of the tapes as a single point charge like in the previous lab? We compare the estimated value of the charge we get in lab 1 versus lab 2. So as you can see, the one on the left is actually the lab 1 the result I got, and the charge per tape turned out to be 1.52 times 10 to the negative 8. On the right I have my model from this lab just now, and the result I got was 3.3 times 10 to the negative 8 coulombs. So both of them are in coulombs. And you can see that the lab 2 result is twice as more, so there is a drastic difference with considering a line charge, which is estimating the entire charge to be concentrated at 1 point. Discussion 2. So discussion 2 asks if these estimates differ and which value is more likely the real value and why. So line charge will actually be closer to reality, just simply because we remove a generality, right? When we consider a charge at 1 point, we're generalizing the charge to be exactly at that point, which is not true. The line charge are closer to reality, where it's distributed along the tape. In reality, it will be distributed across 3D surface, but for the purpose of this lab, it's just a line. So basically, in short, we just reduce generalizations. Sources of error. So some of the sources of error that we could have had in this lab would be uneven charge distribution. So we assume that there's a uniform charge density along a line, but it may clump in patches. So air current or vibration, so small rafts shaking the setup can push the floating tape, and hence kind of disturbing the equilibrium F equals to Fg. Charge leakage, so tapes can lose charge quickly when touched, exposed to warmth or any other oil or substances, so there could be charge leakage there. Mass estimates, so using the 1 gram per meter guideline, Induces uncertainty, so rather just weigh the tape directly. Measurement uncertainty as well, so it's difficult in measuring the precise distance, so there might be few uncertainties that creep into the final result. So anyways, that's it for me. Thank you, and this is Tamesh Shukla signing off for Lab 2. Thank you.